Welcome to Engineers Mindset. So in today's class, we are going to be talking about the Rankine cycle. I will show you what the Rankine cycle is all about and also show you how you're going to obtain your formulas without actually cramming or memorizing them. Just to obtain the formulas, very easy steps from the diagram. Okay, first of all, what is the Rankine cycle? The Rankine cycle is simply a vapor power cycle which converts heat into mechanical energy. So the cycle actually comprises of four different components. We have the boiler, we have the turbine, we have the condenser, and then we have the pump or the compressor. So let's take a look at how these components are being combined to form this cycle. Okay, so we simply have the boiler. Okay, this is the boiler. Okay, we have the turbine. Okay, we have the condenser. And then we have the pump. So this is the boiler, this is the turbine, this is the condenser, this is the pump. Okay, so we simply have this. Now, just like the name implies, a boiler, the function of the boiler is actually to add heat to the system. So we simply have heat addition into the system, call that Q1. So the function of the boiler is actually to add heat into the system. The system could be a working fluid, maybe a fluid inside the boiler. Now, the boiler actually adds heat to this system till it becomes a vapor or simply a steam. It heats up the fluid in the boiler till it becomes a vapor or a steam and have a high dryness fraction of about 1. This steam becomes superheated before coming out from the boiler. So what comes out of the boiler is actually a superheated steam, a vapor, or simply a gas. That's what comes out from the boiler and enters into the turbine. Now, the function of the turbine is actually to remove work from the system. The turbine removes work from the system. Now, recall that what enters the turbine was actually a steam. Now, as the turbine is removing work from the system, a little amount of heat is lost by this steam inside this turbine as state 2. So that simply means that inside the turbine as state 2, what we now have is simply a wet vapor, a mixture of both steam and a little amount of liquid or fluid inside the turbine. Okay, now what comes out from the turbine is still this wet vapor. This wet vapor enters into the condenser at state 3. The function of the condenser is actually to what? Remove heat from the system, just like the name implies, a condenser. The function of the condenser is to remove heat from the system, completely turns this a wet vapor into a liquid or a fluid. It completely turns it into a liquid or a fluid. So it sends this liquid now down to the pump. Okay, the function of the pump is actually to add work to the system. The pump can also be called a compressor. It compresses the fluid or this liquid, compresses back into what? The boiler, and then the cycle continues just like that. So I've said that the boiler actually adds heat to this system. In the boiler, we have water or a fluid. Now, this boiler adds heat to the system at a certain temperature. Simply call this temperature T1 and the pressure at this point also pressure P1. So the state of the boiler is simply called state 1. So this is simply state 1. Okay, so the boiler adds heat to this system till it becomes simply a steam, a gas or a vapor with a high degree of dryness fraction of about 1, and this steam is simply what? Superheated at what? This given temperature T1, which is also called the superheated temperature. So what comes out from the boiler, like I said, is now what? Is now a steam and then enters into the turbine. The turbine actually removes work from the system. So this is simply WT, work done by the turbine. The turbine actually removes work from the system. Okay, so the turbine removes work from the system. Now, like I said earlier, this is actually stage 2, okay, in the turbine. Now I said that inside the turbine, as this work is being removed, a little amount of heat is being lost by the steam, and therefore a certain amount of what fluid or liquid sets in into the steam. It becomes a wet vapor in the turbine. It becomes a wet vapor. So what is coming out from the turbine now is actually a wet vapor, a high amount of steam, but then a little amount of wetness also involved in it. So it's actually a wet vapor. Now this wet vapor enters into the condenser at state 3. So the function of the condenser is always to remove heat from the system. So call that Q2. Okay, the pressure of the condenser is simply pressure at state 2. That's simply P2. The second pressure, sorry. The pressure of the condenser can also be called P2. So the function of the condenser is to remove heat from the system. It removes heat completely from the system, turns this wet vapor into a liquid or a fluid. It becomes completely fluid, and then it sends it to the compressor or the pump. The function of the pump is to actually add work to the system. So we simply call that pump work. The pump actually adds work to the system. It can also be called compressor. It adds work to the system and compresses this fluid. Now it has now become completely fluid. It compresses this fluid back into the boiler. So the state of the condenser is actually state 3. So we simply have this, and then it sends to the pump. The state of the pump is actually state 4. So we simply have this. Now we're going to represent this whole information using a TS diagram. So using a TS diagram, a temperature entropy diagram. This is temperature line, and this is the entropy line. Okay. So in thermodynamics, this is actually how the TS diagram looks like. All the properties of fluid on this region are called the saturated liquid region. So every property of fluid at this point is completely what? Liquid, completely wet. They are completely liquid, okay, at this point. So the properties of steam table, like the enthalpy at this point, is called HF, and the entropy at this point is called SF, while the internal energy at this point can be called UF. So all the property, F there simply stands for fluid, which means all the properties of the steam at this point are completely liquid or fluid. Meanwhile, properties of fluid on this other end are simply called the saturated vapor or the gas line, or also can be called superheated steam. So the enthalpy at this point can be called Hg, entropy at this point can be called Sg, internal energy at this point can be called Ug. So the properties of the steam at this point, these are completely saturated, they are completely superheated, or you can simply call that the gas or the vapor line. Meanwhile, in between is what we call the wet vapor. So in between is what we call the wet vapor. When any property of fluid exists in between the liquid line or the gas line, we simply call that the wet vapor. Okay, so the properties of steam table at this point, like enthalpy can simply be called HFG, internal energy can simply be called UFG, and entropy can simply be called SF G. So we can simply have this. So FG just means a mixture between fluid and gas. So any property of fluid that exists in between here is simply called the wet vapor, which is a mixture of both dryness and wetness at the same time. So there's always a need to find dryness fraction at in between this place. So the dryness fraction at the liquid line is completely 0. Dryness fraction at the gas line is completely 1. Then in between we have a value. So dryness fraction can never exceed 1. It's always between 0 and 1. When it is completely liquid, x here is equal to 0. When it's at the gas or superheated, x is equal to 1. And then when it's in between, then it has to be from either 0 to 1 in between. All right, so we are going to now represent the cycle using the TS diagram. Okay. So I said that the heat is being added in the boiler at stage 1 at a given temperature, which is superheated temperature T1, and also at a given pressure. So we have the heat at stage 1. Okay, this is stage 1. Temperature here is T1, pressure here is P1 at this given state. This is stage 1. Now this heat heats up the fluid till expands into the what turbine. So it heats into the turbine at stage 2. So I said at stage 2 in the turbine, what enters into the turbine initially was a steam with high dryness fraction, as can be seen here. This is a superheated steam, so it's actually outside the gas line, so it's actually a superheated steam. Now, in the turbine, work is being removed from the system, and I said a little amount of heat is lost when work is being removed from the system. As a result, there is now a mixture of both steam and liquid, which I simply call the wet vapor. So you can see that as the two, it exists between the gas and the liquid line. So this is actually what a wet vapor, a mixture of both steam and fluid. So as the two in the turbine is actually a wet vapor. Now the turbine sends this wet vapor down to the condenser at state 3. Okay, the function of the condenser is to completely what? Remove heat from the system and turns it to a liquid. That is why at state 3, you simply have it to be at what? The saturated liquid line. So all the property of the fluid now at state 3 is purely liquid. So turbine sends it to the condenser removes it from the system, turns it to a liquid, send it to state 4, which is at the pump. Okay, so it sends it to the pump at state 4. This is the pump. Okay, so we have this to be the direction of flow. So at state 4, what enters into the pump is completely liquid or completely fluid. That's what enters into the pump. Okay, so this pump now compresses this fluid or this liquid down into the boiler. So it compresses the liquid from state 4 down straight towards the boiler. So you simply have this, okay? So it compresses the fluid back to state 1 and then the cycle continues like that. Alright, so how do you now pick out your formulas without having to cram or memorize them? By simply drawing this cycle, you can always get your formula if you think you forget it. Okay, or if you think you've forgotten it, you can always get it back by simply drawing is make a sketch of this cycle and you can always obtain your formulas. But let's see how it works now. Now I have the heat addition Q1 which enters into the boiler at a given temperature T1, which is fighter temperature, and a given pressure P1. Now, like I said, what is coming out from this boiler is completely what? Steam, having a high dryness fraction and also having is superheated. So therefore, the enthalpy at this point, enthalpy coming out from this boiler is simply H1, and H1 is simply given as what? Hg. We can obtain H1 as at Hg under the given pressure from superheated steam temperature T1. So all we need to do is to go to superheated steam temperature corresponding to the first temperature given to you and then the pressure given to you, which is the pressure of the boiler. Then Hg at that point becomes H1. That is the enthalpy coming out from the boiler. Now, the enthalpy coming out from the turbine itself, this is state 2. Of course, the enthalpy is simply what? H2. But not forgetting that state 2 is a mixture because at state 2 inside the boiler, a little amount of it is lost. So there's a mixture of both there's a mixture of both fluid and vapor. So it means that H2 can actually be gotten as simply HF plus X HFG. So H2 can simply be gotten as this, or simply HF2 plus X2 HFG2. So which means there is always a need to find dryness fraction at state 2. Since this now exists in between the wet vapor, there's a need to find the amount of dryness at that particular point, which is at state 2. So H2 is equal to this. Meanwhile, what is coming out from the condenser now, H2 is entering the condenser, and what is coming out, enthalpy coming out from the condenser becomes H3, and H3 is simply HF3 under the given pressure of the condenser. Okay, so HF simply because in the condenser, it turns it completely to what? Liquid. So which means dryness fraction is 0, and if X is 0, it means HFG is completely gone. That part is gone. You have 0 at that part. So you're simply left with what? HF. So H3 is simply what? HF as state 3. Normally, it's supposed to be H3 equals HF3 plus X3 HFG as state 3. But as state 3 from the TS diagram, what is in the boiler is completely what? Liquid. What is in the condenser is completely liquid. The condenser completely removes the heat and turns it to a liquid. So which means it doesn't have a dryness fraction. And since it exists here, it means X3 is 0. So this part of the equation is actually gone. This is 0. So you're simply left with what? HF3. Okay. So that simply means that H3 is equal to HF3 at the given what? At the given pressure of the condenser. Okay. So what enters the pump is actually HF3, and what leaves the pump, remember the pump is also completely liquid. So pump compresses this liquid back into the boiler. So it is actually was still HF4, as can be seen here. It is purely on the liquid line. So it still has HF4 without a dryness fraction. So these are the enthalpies of each of what the stages in the turbine, the boiler, the condenser, and then the pump work. Now, how do you now obtain your formulas? First is the heat addition in the boiler. So let's get down now. Heat addition, okay, by boiler. So you take a look at the boiler. For energy balance, the sum of the parameters entering into the boiler must be equal to the sum of the parameters leaving the boiler. The boiler actually what supplies heat, so heat is actually being added into the boiler. So I have it going into the boiler. I have here HF4 also entering into the boiler. Meanwhile, I have H1 leaving the boiler. So the sum of the parameters entering the boiler must be equal to the sum of the parameters leaving the boiler. So I simply have the heat entering the boiler Q1 plus HF4 entering the boiler, and that's simply equal to what H1 leaving the boiler. So therefore, I can now find the heat supply, which is Q1, as simply equal to sending HF4 over here. It simply becomes H1 minus HF4. This becomes the heat supplied by the boiler. Moving on to the turbine. In the turbine, of course, we have H1 entering the turbine. The turbine actually removes work from the system, and then we also have H2 leaving the turbine. So we have the work done and H2 actually leaving the turbine. Meanwhile, H1 is actually entering the turbine. So for energy balance, the sum of the parameters entering into the turbine equals the sum of the parameters leaving the turbine. So I simply have H1 entering the turbine. Okay, turbine work. Okay, so I simply have H1 entering the turbine, and that's equal to turbine work leaving the turbine, okay, plus H2 also leaving the turbine. So I can make turbine work subject. That simply means WT is now equal to, it becomes H1 minus H2, sending H2 over here, it becomes H1 minus H2. So this is the formula for the work done by the turbine, okay, simply difference in enthalpy at state 1 and that at state 2. Now, same thing at the condenser. The function of the condenser is actually to what? Remove heat from the system. So heat removed or heat rejected by condenser. Okay, heat rejected by condenser. So the heat rejected by condenser, of course, just like in the first case, the sum of the parameters entering into the condenser must be equal to the sum of the parameters leaving the condenser for energy balance. I have H2 entering into the condenser, so simply put that down, H2, and that's equal to, I have H3 is leaving, I also have heat to be leaving, Q2 leaving, so condenser removes heat from the system. Now recall that heat removed from a system is actually what? Always negative. So for that reason, I'll simply have minus Q2. Negative sign because heat is removed from the system. Heat removal from the system is always a negative heat. And then I have what? H3, which is simply HF3. H3 is equal to HF3, leaving the condenser. So simply plus HF3. So I will simply make Q2 subject of the formula. Simply send minus Q2 over to this side of the equation. Negative sign cross an equal to sign becomes positive. So I'll simply have Q2 to be equal to, here I am left with HF3. So I simply send H2 over here. Positive sign cross an equal to sign becomes negative. So I'll have HF3 minus H2. So this is always going to be a negative heat. This is always going to be a negative heat because heat removed from a system is always negative. But the formula for heat rejected by the condenser is simply HF3 minus H2. And finally is the pump. Okay, most cases, in fact, in major cases, the pump work is usually neglected because it has a very small value as compared to the turbine work. So it's almost not noticeable. So we usually neglect the pump work. But I'll still give the formula for the pump work just for formality's sake. But I don't think in these videos or subsequent videos we're going to be doing, we're going to make use of the pump work. But I'll still state the formulas just for formality's sake. Okay. So let's do that over the other side. All right, so pump work. So just like in the previous cases too, the sum of all the parameters entering into the pump equals what is leaving the pump. I have HF3 entering the pump, I have WP entering the pump, I have HF4 leaving the pump. So sum of what is entering is WP is entering the pump, okay, plus HF3 is also entering the pump, and that's equal to HF4 leaving the pump. Therefore, the pump work can now be considered simply as HF3 minus HF4. If I simply send HF3 over here, it becomes HF4 minus HF3. So this is actually the formula for the pump work, or the work done by the pump. That gives us the formula for the pump work. Now, having known this now, like I said earlier, the pump work is usually neglected. We usually neglect the pump work simply because it has a very minor value compared to the turbine work. So it is usually neglected. Now, there's another formula for the pump work. Pump work can also be given as minus V dP. So take note, pump work must always be negative. Always, it must always be negative. So pump work can also be given as minus V times change in pressure. If you're given the volume of the gas, and you also, or the fluid, you're also giving the difference in pressure of the fluid, of course, you can always find the pump work using that equation, but the value is always a very small value, so we usually neglect pump work. All right, so having known this now, the worst thing that could be asked for you to find using the Rankine cycle could be the cycle efficiency. Okay, so cycle efficiency. Okay, the Rankine cycle efficiency is simply the net work all over the heat supply, which is Q1. Q1 is heat supplied multiplied by 100%. Okay, so therefore efficiency is now equal to, of course, so the network is actually the sum of the turbine work and the pump work. So I'll simply have WT plus pump work all over heat supplied multiplied by 100%. And in the absence of the turbine work, like I said, and in the absence of the pump work, like I said, the pump work is usually neglected because it has a very small value. You can also write the efficiency, okay, as simply turbine work all over heat supplied multiplied by 100%. So that's how you're able to figure out your formulas without even having to, go through rigorous process of trying to cram or trying to memorize the formulas. You can just figure it out by simply making a minute of what a small sketch of a diagram. You can be able to pick out your formulas from the diagram. Also, if you observe the TS diagram, notice that if I trace a line from state 4 to state 3 down to this entropy line, I have that state 4 and state 3 are touching the entropy line. This is temperature line and this is the entropy line. So since state 4 and state 3 are touching the entropy line, it simply means process 3 to process 4 is actually an adiabatic process, which can also be called a constant entropy process. And as such, entropy at state 3 is equal to entropy at state 4. So we can simply say x3 equals x4. Similarly, state 1 and state 2 is also, if I trace this line down to the entropy line, which is that state 1 and state 2 are touching the entropy line. So it also means that state 1 and state 2 is also an adiabatic process, or simply a constant entropy process. So we can simply also say S1 is also equal to S. So these are additional formulas that can be used when analyzing Rankine cycle. All right, guys, I hope you find the video very interesting. Please, if you do, I would like to get your thoughts in the comment section. And of course, if you have any questions at all to ask on Rankine cycle, you can always say that in the comment section, and I promise to respond to all your questions. In the next video, we'll start doing analysis and calculations of the Rankine cycle using everything we've learned over here. There. All right, guys. Thanks and cheers.